Hi everybody, welcome to another CCOM seminar. Today's seminar speaker is Glen. Glen is the lieutenant with the National Oceanic and Atmospheric Administration Commission's Officer Corps, and he's the team lead here at the Integrated Ocean and Coastal Mapping Center. Integrated Ocean and Coastal Mapping, IOCM Center. He comes to us from the NOAA ship Fairweather, which primarily surveys off the coast of Alaska. And he has a BS in physics, and he actually got his master's here in ocean mapping in 2005. And now he's going to talk to us about real-time measurements in the ellipsoid and turbine.
Thank you. Okay, so I guess you can see my name's on the slide here, but there have been a number of people that have been involved with this. Jack Riley in particular, who's at HSTP, has had a lot to do with this. And there's been a lot of people working on surveying the ellipsoid in the field that have been thinking about this for a number of years. So hopefully there's a growing number of people within NOAA that have been thinking about this and understanding, but I certainly encourage further discussion about this because it's kind of a growing topic right now. It's not something that we really have figured out entirely. So what this is about is trying to make measurements between the chart datum and the ellipsoid as you survey. And the reason this is important is basically in the context of ellipsoidally referenced survey. You want to know your datum separation so that when you completed your survey to the ellipsoid datum, you have a way back to your chart datum. So with that said, I'm going to take a step back and give you a quick overview of traditional water level survey and ellipsoidally referenced survey, just so that there's kind of a common understanding of some of the vocabulary I'm using, and then proceed to talk about the main focus here, which is ellipsoidally referenced zone tides is basically what we're calling this method, ERZT, which basically is trying to take all your measurements as you go around, all your navigation points, and turn them into a surface that represents the difference between the ellipsoid and your chart data. Okay, so, and hopefully by the time I've gotten through these first two topics, this general concept will kind of fall out. And then I'm just going to go through the steps involved. So people who get the general concept and don't care from there, there's certainly people who have talked to me about this, and once they got through this, they didn't want to know about this part. So I'll warn you before we do this so that you can shut your brain off. And then some of the preliminary results from looking at this are pretty interesting. But okay, so traditional surveys, vessel offsets is a big deal. Basically everything on the vessel is referenced to the primary reference point. And so things like your sounder, you have to know where that is relative to the primary reference point, so that everything else, like your positioning system, can correctly locate, where your soundings are. If you're towing a side scan, you want to know where your tow point is on the vessel. So that primary reference point is of utmost importance, and how everything is referenced to that is really important. So obviously, if you want to know how deep it is, though, you don't really care where this reference point is. What you care about is where the water line on the vessel is. So the water line on the vessel is a static water line. So if the vessel is just sitting still, you basically can go through some typical survey procedures to get an understanding of where the water line is relative to that reference point. But unfortunately, the vessel moves when you're surveying. So it's not quite that straightforward. You also need to understand how the vessel settles depending upon the speed it's traveling through the water. So there's a number of ways to go about defining a table that basically correlates your speed with what this difference is, which I'm not going to get into here, but there are a number of ways to do that. So then you take the timestamps from when you're collecting your data, each of your soundings, every time you ping, and you convert that static, or your static water level, which now has a dynamic water level applied to it, and then you have an offset to your chart data that you're applying also. Through the timestamp, you say, well, I can have a pretty good estimate of what the water level was where I was surveying based on the tide model and based on what gauges we're reading at some remote location from where the survey is. But as you can imagine, there's a number of issues that arise from these kinds of offsets. The static water level is heavily influenced by the loading conditions, especially in a situation with a small launch. You put 5 people on there instead of 2, or even with large vessels, you burn a bunch of fuel. It can drastically change the water line of the vessel. So that changes over the course of a survey. So it's something you have to keep track of and you want to update, but it kind of becomes this discrete change, and certainly isn't ideal. This vessel settlement measurement is also somewhat problematic because it's difficult to measure your speed through the water unless you have a specialized sensor for exactly that purpose. So this is generally approximated by looking at your speed over ground from the GPS. But if you're in any kind of current, your speed over ground is pretty different than your speed through the water. So this vessel settlement measurement can be off. And then getting chart datum can be a little bit weird. Depending upon the distance to your tide model, if you have things like storm surge going on, you can have very different conditions at your survey location than are actually going on at the gauge. So how the gauge measurements get propagated to the survey location can end up being less than exact. So that's a little bit about this side, which is traditional water level survey methods. We've got the chart datum to water level reference point, and then the seafloor offset from measured from the reference point through the transducer on the ship. So the other side is this ellipsoidally reference survey, which basically goes from the ellipsoid, which is a mathematical model of the Earth, down to the reference point through some software that we use. PAUSEPAC basically uses inertially aided post-process kinematics to define the location of that reference point within a few centimeters, actually, relative to the ellipsoid. So this is kind of what ERS looks like. So we have our typical method here, where you have your tide gauge over here, have your chart datum, and then you have location of the vessel, the water line in the vessel, and then that's located through the methods we just mentioned. But when you're surveying the ellipsoid, you generally have some sort of a base station, and your satellite vehicles, which you then use to position the ship. So using GPS isn't actually just GPS isn't accurate enough for typical survey methods. So you actually have to use the space station to use like a double differencing method to improve that height, and that's how you get that centimeter level accuracy. So looking at this, you might say, okay, well, we have this height and we can get this, so why don't we just get the difference here? Well, it turns out that it's not that easy because, in fact, because of the shape of the geoid and sea surface topography, these two things aren't parallel, which means that it's just because we get the height over here doesn't mean that that's the same distance over here. So benefits of ERS mean that we basically get rid of this water level reference, because we're going through the antenna on the vessel, we're using the motion sensor on the vessel to get this centimeter level positioning. So we get rid of a lot of those errors I was talking about, having to do with the tide, having to do with the settlement, and then also the static water level. And basically the blunders that you run into when you have busts associated with those waterline measurements means that your surfacing algorithm isn't trying to deal with those blunders, which makes a big difference when you're trying to process the survey. And it also means that you can count for your uncertainty better, because rather than just kind of a static uncertainty that say, well, this is generally the error we get associated with our dynamic draft or our tide model, PAUSEPAC produces a real-time uncertainty associated with your height, which is actually pretty good. So it's nice to have that uncertainty be dynamic, because it means that you're modeling your surface algorithms that model the surface can do a much better job of trying to account for separation in the soundings to figure out where the bottom actually is. The other big advantage from a field perspective is that you're not waiting for your final tides or final zoning to actually produce your final surfaces. If you're doing ERS, as soon as you have your ellipsoid height of your vessel, you can start producing your final surfaces, which is all the cleaning and combining, creating a surface, which really speeds up the process. Waiting for tide slows everything down. It means you generally produce a first surface, and then a few weeks after the survey's over, you have to go back and produce another surface. So doing this once is a pretty big benefit. So the issue with ERS, though, is getting back to the chart datum. The ellipsoid is pretty meaningless if you try to put your ellipsoid height on the chart. Clearly, you know, the QE2 would have been, anyway. So the methods that we have right now for approved getting back to the chart from our ellipsoid height is Datum, which I understand the geodesy class talked a little bit about yesterday. And these are the coverage areas. And as you can see, we're missing it up here in New England. We don't have it here in Texas. But the other place that NOAA is currently doing a lot of surveys in Alaska, and there is no Datum in Alaska. So it's a huge area where we're sending our ships, which kind of makes surveying the ellipsoid not possible. So that's where this ERZT method comes in. Anywhere you don't have Datum, you would be trying to do this ERZT method. For really small surveys, you could also do a single offset, and that basically just means the slope of the geoid relative to the ellipsoid is small enough that you don't have any substantial difference there over the course of the survey. All right, so moving on here. This is where we start shifting to ERZT. So we can get our ellipsoid height relative to the reference point of the vessel. We know how to get the chart datum relative to the reference point of the vessel. And these are approved methods. We're going to use these because they're all we have when we go out to survey in somewhere like Alaska. We have our chart datum through our tide model. We have all our water level offsets. We know that they're flawed, but those are the approved methods. So if we apply them to our ellipsoid height, that essentially means you can get from the ellipsoid to your chart datum for each of your navigation points. So your ellipsoid height that you're producing as you go along, if you just apply a water level and then apply a chart datum, you essentially get measurements as you go along of that difference. And then essentially you can go along and smooth them all. And you get a surface that would represent something like Datum. That would be this difference between the ellipsoid and your chart datum. And so how we get there, these are the different components. We kind of talked about them all already, but I'm going to continue to beat this just to make it as clear as possible. So we have our ellipsoid height, which is coming from our smooth best estimate of trajectory. So that's what comes out of POSPAC. And our water level, which we get from our heave, that comes from a POS file. Static water level, we talked about that. Settlement, that's coming from our settlement table, and our velocity, which comes out of our smooth best estimate of trajectory. And we also have our tide model. So at this point, if you understand all that, and you don't really want to look at all the details, this is where I actually go through step by step how this whole process happens. So this is the SBET right here, basically. Smooth best estimate of trajectory. This is where the vessel was over the course of a survey day. So you can see there's a lot of heave artifacts in here. Clearly there's kind of a tide artifact. But basically the vessel was traveling on this trajectory over the course of the day. So that,
relative to the ellipsoid.
Relative to the ellipsoid, correct. Thank you. And so that's that reference point right there. And so if we take the heave out, we get a much smoother signal. You still have the tide signal in there, but we also need to account for the dynamic draft and the static draft of the vessel. I'm sorry, the vessel settlement. And so vessel settlement is a function of speed. So basically, if we take the velocity over the course of the day, we can use the table and produce signal that looks something like this. And so you can see the vessel was changing speed here, probably turning around and going on a different line. So it had a significantly different draft than it might have when it was just surveying along. And so if we combine that with the static water level of the vessel, you get this offset here. And so we take the curve we had a couple slides ago, which was the smooth best estimate of trajectory with the heave removed. We basically just correct to the water line of the vessel. So now we've gone from the ellipsoid to the vessel water line. But clearly there's still that tidal signature in there. And so this is what the tide looks like for where the vessel was over the course of that day. So these are the vessel lines on the chart, and these are the tide zones. And basically you can see as the vessel was traveling through tide zones, there's these little hitches in the tide correction that we would normally use. But basically this is just a function of position and time. So you can back this back out in a relatively straightforward manner. And so if we just add that tide correction to our signal after we have applied heave in the water line, we get out something like this, which is essentially the difference between our chart datum and the ellipsoid. See there. And so that's pretty much all there is to it. I went through it step by step there, but in fact all those steps happen all at once. Yep.
Can you go back
Sure.
3 slides or so? Yeah. Why don't you just fit a smooth curve to that
Put a smooth curve to this.
to get the tide signal?
You could, because the vessel's not staying in the same place, you wouldn't get a tide signature like you might expect.
Well, it seems to me you get a more accurate one than the zone model.
You
And
could.
those steps aren't real.
Well, okay, so there are probably a number of ways to come at how to correct the tide issue. You could actually use the vessel as some kind of a tide buoy to try to actually predict what level the tide was at in certain locations. But part of the point of doing it with the current method is that we're using currently approved methods, which means we can take this and we can run with it right now, as opposed to having to go through a whole other procedure of coming with tides a different direction. But certainly there are other ways to skin that cat. Okay, so
Wouldn't that assume that the ellipsoid and the water height are parallel? Didn't you say earlier that they aren't necessarily?
well, he was just saying essentially smooth it. So you
But you could end up with a bias there.
could end up with a bias. So you can see there's a small slope there. This is because the vessel was slowly moving north over the course of this day. But you could smooth this in such a fashion, having some prior knowledge of the constituents of the tide would probably.
But you missed that slope.
Maybe. We can talk about it. Yeah.
Glenn, now I'm confused. I didn't think you were treating that separation between the ellipsoid and the chart datum as a constant over space. You're not, right?
Correct.
That can vary from place to place.
Well, but it's essentially only varying between zones because we're correcting by zone, essentially. You're assuming that the tide correction by zone is the same. So when you change zones, it's not the same, right? That's where these little hitches come. But
So you're using one offset per zone, or?
well, the tide zones essentially have one phase and one multiplier times whatever's going on at the gauge. And so the gauge is essentially influencing what that offset is, and so it's changing over the course of the day. This is exactly how you would normally do tides.
So Glenn, you're only making you're making a ellipsoid to the chart datum single value for each tide zone. So each tide zone gets a different single value?
That's more or less the result. But hold on, we'll see a little bit more later, I think, that shows why that's not actually what ends up happening. But that's essentially the effect at this point. Once you start smoothing, you essentially are smoothing across these boundaries. But we'll get there. Okay, so this process is currently happening through Hydro, because Hydro has a tide correction package in it. Hydro is a NOAA essentially that does lots of things. Tide correction is one of them. But basically, combining the pause file, which has the heave in it, the SBET, which has our ellipsoid height and velocity in it, with tables for dynamic draft, which should say settlement, but also static draft, and then just does the tide correction. And so just open a bunch of files that have all that information, crunch through, do the tide correction, and basically spits out an XYZ file, which currently I'm just writing to an IBS format because Fledermaus has a weighted moving average way of making the surface that is advantageous for doing this process. And it's also a binary format, so it's a lot smaller. I'm also writing out an XYU file, so XY and uncertainty, basically combining the uncertainties from all those different contributions with the root sum square process. but this is essentially what you get out. It's just a time series. And you can see this one's a little more noisy than the one we were just looking at. It has spikes like this. But these spikes are pretty certainly associated with the SBET. Because your high frequency issues associated with GPS, which varies a fair amount in the short time frame, produces a lot of these kinds of effects.
Glen? There's
Yep.
also some more systematic looking things. Is that from going into the different zones, or is the little to your right?
These ones here?
Yeah, and there's excursions there, yeah.
Yep, I haven't looked at what those particulars are for this particular file. You know, a lot of this, because it's varying both in space and time, it's difficult to get a handle on what all those problems are necessarily when looking at it like this. But if you look at it like this, you can start to see where some of those different things might come from. Partly because you're just looking at it all relative to each other. So this clearly is a bust in the SBET. And you can see there's a lot of spikiness here on the surface. This is two different vessels that did this survey. This is the Fairweather in 2010. And the height of a lot of these things here is on the order of like 6 centimeters. So this is, or 10 centimeters. So it's on the, you know, it's exaggerated in a very large fashion. But there's a slope there, pretty clear slope. And so if we average this, basically I did a 1 kilometer moving average. One surface there is VDatum, and the other one is the ERZT surface. So even though you have those little hitches coming from your tide zoning, and even though the vessel may have gone to some of those places multiple times and gotten slightly different answers, when you average it out, all those things go away. It's just like if you take a position for a long period of time. The geoid varies so slowly, and we put so many lines in small areas that essentially you average out a lot of that stuff. Which is good because I think you get a much better product. You don't have a lot of those hitches that would normally be in your surface. But you might see them in your uncertainty, which is I think where they actually belong. So for that particular surface we were just looking at, with a 1 kilometer moving average difference with VDatum, you end up with about a centimeter difference in the mean, and you end up about 5 centimeter difference for standard deviation. You can see the range here is a little bit larger than I might like, but I think that's partly because of how I'm going about doing the smoothing process. I think there are better ways to do that, maybe a regression technique, but that's something that still needs to be improved.
What's an acceptable value?
I would say anything under 15 centimeters. Just because
Say that again?
15 centimeters, just because it starts to get into the range of uncertainty for what VDatum actually is. But generally, we're accepting our SBETs when they have an uncertainty less than 6 or 7 centimeters.
Would it make sense to, as you're going through this averaging process, to basically cube it and then get?
I don't think so, because you shouldn't actually have separate hypotheses. It should be pretty much normally distributed in localized areas.
But if you have one strong hypothesis, that would be your, you can set really small constraints over when you get triggered on the hypothesis. And you get your smooth surface and an uncertainty associated with it.
Let's come back to that in a minute. Sorry to keep putting it out there. So just another example here. This is the TJ from Chesapeake Bay, also from 2010. So this is the launches. The ship isn't actually in here because the ship had other issues. They had a variation on the order of, I think it was like half a meter. So just the launches, though, you can see also agrees with VDatum really well in Chesapeake Bay. And so that's basically the mean was less than 1 centimeter. Standard deviation was around 3 centimeters, and the difference between the two, I would say, is within an acceptable range, the absolute difference range. So this is getting to more kind of some of the things that have been coming up here, which is what happens when you have these kinds of issues. So this right here is actually Tammy's survey from 2009 in Alaska. This is Prince William Sound, and we had about a 1/2 meter offset in the surface. This is down in this area, coming around this point. And this is a fairly small opening here out to the open ocean, and there's a lot of water that comes
What
through
two
here.
surfaces are offset here?
So this basically is the bathymetric surface. And this is exactly the kind of problem that traditional tide packages cause, is because you end up with things like this, and then your survey manager spends a lot of time trying to chase down where this problem came from. And a lot of the time, these kinds of issues just get swept under the tide rug because we don't have any other way to look at them. They're just in the bathymetric surface.
So that's two pieces of the same surface that don't agree?
Correct.
Okay.
And that happens in Alaska fairly regularly.
Are they two lines that are separated in time?
Yeah, essentially they're data from one day and the next day.
Okay.
Same launch, 2 different days.
Yep.
For
And
your,
so, yep, go ahead.
for your surveys in Alaska, did you use a single base station, or did you have a network of, say, 4 stations? Or-
This is reference to the tide.
Yeah, I realized that,
Mhm.
but I was wondering.
Depends on the
GPS.
survey. In some places you have enough stations to do a network, but a lot of the time we end up using a single station.
So there's no ERS information in this picture?
Correct. This is all tide related. This right here is the ERZT surface that I created using this data, but there's no VDatum to compare it to. So the question is, could this replace VDatum in this place?
What's that offset, the vertical offset over there on the right?
1/2 meter. Yeah. So I guess really what this gets back to is if we're averaging this all out, what you want to know is what the uncertainty in the transformation is. And so like Larry's bringing up, well, there's different ways to do the tide. Or Andy's bringing up, well, or I'm sorry, Larry was also saying, what if you cubed it? Well, really what you want to know is if you average it out, what's the residual variation in the surface? I mean, if you have these tide busts that are 1/2 meter, you should be able to say, well, I think that, right about in the middle is as good a guess as I'm going to get. But the uncertainty in that transformation should probably be fairly large. And that's probably a better way of describing the uncertainty than we're currently doing, which is basically just saying, well, there's a tide bust. We have this hitch on the surface, but there's nothing we can do about it. We just kind of stuff it into the survey pipeline and let it go. The uncertainty never changes, even though we have a known problem there, because there's no mechanism for us to describe it. So there are 2 ways to look at the uncertainty. One it would be to combine the components as we usually would, the heave, the tide, the dynamic draft, all those things, which I have an example of. Or we look at the variation from the mean, which I was just describing. So this is if you combine them all, you can see it's static. Well, it's because the heave doesn't really change very much, and the uncertainty of your tide doesn't change, and uncertainty in your static draft, your settlement doesn't change. So this is pretty static with the exception of the contribution from the SBET, which is the only one that really says, wait a minute, I have a problem here, I don't have a very good position. And you can see that doesn't describe really what's going on. So this is that area where I was showing you the 1/2 meter bust is from. So you probably can't see this very well, but that's 1/2 meter, and the middle's right there. So from this line down here to this top of the line here is around a 1/2 meter. Like the issue, or the problem with the bathymetric surface is coming from the difference between the tide on separate days, as we might have guessed. But we can actually see it. That's the advantage, is that because you have referenced all your tidal measurements to the ellipsoid, you could look at this and say, well, my cross line that comes along here suddenly jumps up and down. You can see that it doesn't agree. So by tide referencing, by ellipsoidally referencing your tides, you can see these problems here and not in your bathymetric surface, which means your bathymetric surface goes through the pipeline, no blunders, that all works great. And now you're looking at your datum problems in a kind of a separate arena. The other advantage is that these are all problems that the ship really can't fix. The ship can't fix tide problems. So kind of what I said when I gave this talk a few weeks ago was, well, maybe this problem isn't something that needs to be fixed on the ship. Maybe this should be fixed somewhere else. If the surface is good, it should be allowed off the ship. And this kind of datum transformation, they produce it, but if they can't come up with new tide zones to make it better, then it goes unless somebody raises a red flag and says, well, wait a minute, let's tweak the zones, let's reproduce this surface. so that when we bring the ellipsoid surface back down to chart datum, we end up with lower uncertainty. So what we were just seeing there, you can see the high frequency issues were still there that come from the ellipsoid solution. The low frequency issues are pretty clearly from your water level correction. So it could be that there was really high currents from your dynamic draft, but my guess is probably something to do with the tide model in that particular location because I happen to know how far away some of those tide gauges were, and in very different environments than where we were actually surveying. And I think that trying to do some kind of a regression technique to produce the surface and then look at the residuals to get an understanding of that variation in the surface is the way to go. I think that if you cube it, you're probably pulling out a lot of those kinds of things that you want to have in there so that you really understand what the uncertainty in your water level measurement is. Yeah, that makes sense?
I think it'll get you the same answer quickly.
Okay. Well,
But I agree, you'll have
because
less understanding.
I think what's important is that not only are you getting a better answer, but you know how good your answer is. And that to me is just as important as getting a good answer. So this is generally what the workflow for ERS I think should look like. The basic idea is that you take your raw soundings, your SBET, make process soundings, with your SVP, and then you create your ERS surface, and then you use your tide model and waterline with your SBET to create the separation surface. And those create your product that you would give to MCD. But these are actually what get archived, because this surface is as good as the data gets. And this surface can improve with time, either by tweaking your tide model or because VDatum comes along and replaces this altogether.
Glenn, is that your suggestion, or is that what's actually happening right now?
I think that's what's going to happen.
What's happening now?
Right now, we are not doing any of this, really. Basically, if we do a survey to the ellipsoid, the separation measurement gets injected during the creation of the process soundings. So the process soundings are always to the tidal datum. And so you end up with whatever was going on here as part of the process soundings. When you create your grid, it's always to your chart data. The advantage of saving your survey to the ellipsoid is that it's useful for other users. There are people that are likely to use an ellipsoid surface, and mean lower low water really has no meaning. So I think this should be an archive product. And I think that as this gets updated, this is something that could actually be created on the fly. So I think that there's advantages there. So, advantages to this method. You're maintaining all your data to the ellipsoid, which means your uncertainty is as good as it gets. I think that your data is more useful to more people because it's on the ellipsoid, and your datum estimates can be improved with time. You can compute your ellipsoid to chart datum separation using real data. And I think that, to me, is the key here. There are people who have looked at this and said, well, to me, those are real measurements, so I would take that over a model any day. And I think that there are problems here which are clearly coming out, but at least they're known problems. And I take a problem I know over one I don't any day.
I thought ignorance was bliss.
Yeah. So, let's see. What is that? Estimate of uncertainty and transformation from real measurements. So, I think that by looking at the variation of the surface, you get a much better estimate of what your uncertainty is. Covered that. Remove water level issues from the original sounding set, improve the grading process. I mentioned how much time the people who are processing surveys on board end up chasing problems and end up sweeping them under one rug or another because we don't actually have the ability to troubleshoot waterline reference issues. And I think that this improves that. And so because we can produce our final surface right away, I think this eventually would speed up the process. Currently, because we don't have a workflow that does this in any kind of smooth fashion. Things are a little disconnected, but I think that once we get this working, I think this will actually speed up how the whole survey process happens. So the disadvantages currently is that we go to the ellipsoid using our SBET, but to get to our water level data, we basically have to go back down to the reference point. So you're basically using the uncertainty there twice. So that's a negative, but I think that can be fixed. But with this method, you never get rid of both the ellipsoid uncertainty, your ellipsoid height uncertainty, and your chart datum uncertainty. Those are both residing there. So your uncertainty in your final surface that's to chart datum actually ends up being slightly higher than it might have been if you had just gone to the ellipsoid. But I think you're ending up with a much better product. So I think that that's okay. So this change to the workflow, I think that that is just a question of time. I think that if we improve the workflow and everybody gets used to it on the ship, I don't think it really is a problem. But the change is always tough at first. And a lot of people think that because you need a tide model to do this method is a negative. A lot of people just want to be able to have V-datum and do a survey to the ellipsoid and not have to worry about tides at all. But the fact is anywhere that you go that you don't have V-datum, you're going to need a tide model anyway. So it's just kind of a fact of working where there isn't V-datum. So if you want to survey to a chart datum, you got to have tides.
Could you explain again to me why you're not carrying along all the errors in your tide model in your final product anyway?
You are in the final product that actually is to the chart datum because it's coming through with a ERZT product, but your survey to the ellipsoid does not have the uncertainty associated with tide. So your archive products are much cleaner and can be improved with time. Your final product that would go to MCD and end up on the chart would have the uncertainty associated with tide.
So are you?
So this product.
So the next time you go back to this area and there's still no V-datum, what are you going to do next time?
The next time I would go back and remake the surface. I would, everywhere you go, when you come on the ship at night, you create this SBET. Basically, you chuck this SBET in a folder with your pause file and a couple other things like your settlement table and your static draft offset, and you just let it chug for 20 minutes and this pops out. So anywhere you survey, you end up with this difference.
Why in the world wouldn't you compare that with the previous one that you got from that area? And
I think
even
you
do
could
something
compare
like
it.
Average the two. Or
Combined.
Well, I think it depends on where you're working. There are places where the tides could change significantly, either because of places we work where there are glaciers. If there's significant change in the glacier, that can change how the tide is.
but the
pretty
difference between the
significantly.
tide datum and the ellipsoid shouldn't change.
Well, your sea surface topography could change significantly.
Sea height changes what?
Your sea height could change, but that shouldn't really change your.
It wouldn't change the constituents, but it would change your.
Could change the tidal datum itself.
Tidal datum.
That's not what you're talking about, though. I mean, the difference between that tidal datum surface, which once it's established over that 19-year period, then that's a fixed surface, and the difference from that to the ellipsoid varies in space, but it's not varying temporally once it's established.
They're updating the chart datum, or they're updating mean lower low water in Alaska, I think, every 5 years now, because of isostatic rebound up there being as fast as it is.
So they're doing new epochs every 5 years.
Okay, so then you're saying don't compare across different epochs, but I was making the assumption that you've come back within the same.
Do I think it'd be
epoch.
interesting? Sure. I would use the most recent product. I would use whatever I just surveyed.
You could
But-
look at, sorry,
Oh, go ahead.
you could look at it over time to see what's happening.
Yeah, that'd be very interesting.
That'd be a very interesting thing to look at.
We just tacitly make the assumption that things kind of stuff.
Right. So I think that there are a number of other uses for this, and I think the one we're kind of touching on here is, are there other people who could use this product? Certainly, V-datum verification is one thing, Anywhere we're going right now, we have to verify VDatum. So essentially what they're doing is they're going through and doing the entire processing workflow to the chart datum, and then doing the entire processing workflow to the chart datum through VDatum, and then comparing the two surfaces, which is a huge amount of overhead on the ship. But essentially, if you compute this surface, you're doing that process because you're essentially checking that chart datum to ellipsoid offset, and then you just compare that directly to VDatum, exactly like I did here. So this speeds up the whole verification process, for one, but.
So let me get back to Larry's question about smoothing out.
Okay.
Could you not smooth out your results and improve the tide model in this process?
Well, so here's what I think essentially is going on. You know, we go through and we essentially have a bunch of points. And so this is what we're measuring. And the tide model essentially is creating zones across these areas. So this correction here, you end up with a surface that is disjointed. But because we're smoothing this, I think that jumpiness goes away. There's so many points associated with, even though the tide zones create kind of a hitch here, we essentially smooth it all out because we're doing this.
Yeah, but there's a difference between increasing the resolution of the grids in the tide model and actually fixing the model. So part of the problem is that the model is wrong, and part of the problem is that it's zoned. So the zoning, it seems like, you know, they could smooth the zoning out by just making finer resolution of the zones, but is it possible to actually sort of fix the model?
Well, I think that would be part of, I think you could probably create a tool that took this data and looked at the variation in an area, and you could use that to then essentially try to rebuild the tides. So if you have, you know, you have a tidal signature and you survey here, and the tide model said, well, you know, this is where you were, but you were actually getting measurements like this, and then when you were in that same zone, you were actually something more like this. You could go back and try to look at the residuals for each tide zone and help troubleshoot probably what it should have been reading, or what you should have been getting. But I don't think that you can ever really create a tidal model using this. I think that in the end, you don't have enough information.
Seems like an undetermined problem.
And so I think the right thing to do is just say, use the tide zones and then compute an uncertainty associated with it. And if you want to update tide zones and then try to, you know, make that shrink your uncertainty, then great. But I think it's a troubleshooting tool. I don't think it's a solution.
Once your archive has been built up with enough data over a long period of time, it might be more possible.
Could be.
But do you see this as a transition until VDatum's everywhere?
Yes. And in fact, at this point, it's approved, and the NOAA vessels are going to try to do it this season.
Going back to that last line,
Yep.
you've listed tsunami modeling as application. What you want with you're talking about the bathymetry that goes into a tsunami model, is that right?
I think the bathymetry is an IOCM type product that would help with tsunami modeling. I think the ERZT product could help you understand the separation between the ellipsoid and mean lower low water close to the coast. And so where they go along with a GPS and get a GPS height on the coast, you could essentially extend the model up a little bit. You don't want to go too far, obviously.
Isn't that what we were just talking about?
So I think that it could help you understand like how a tsunami would come ashore, because you would have an understanding of what your I mean, it doesn't even have to be mean lower low water. You could use whatever tide model. You could do mean sea level. You could do mean high water. I mean, it's all in how you compute the surface.
It would actually be, for a tsunami model, it would be mean sea level, because the topographic maps are relative to mean sea level.
Right.
You want to make that seamless connection at the beach.
Have you looked at all at the differences between your levels and the geoid rather than the ellipsoid?
No, I have not. The places that I had something really to compare to, that there was a good geoid, you know, there's already VDatum, so it was easier for me just to compare it straight to the water level. Some of the people that worked in the VDatum team expressed some concern because they said, well, some of those offsets you're seeing are probably just because the tide model you're using and the tide model we're using is slightly different. And I was like, okay, well, we're still within centimeters, so as far as something that right now is just being done in the spare time, that's pretty good. So, there's certainly a lot of other things to investigate here. In places like Alaska, where there isn't VDatum and you might do that kind of comparison, I don't think the geoid, I think if the geoid was actually flown over Prince William Sound, it was like in the last year. And so yeah.
What is the geoidal model that they're using primarily in VDatum? Yeah.
I think you can select what model you use, so it's up to you.
99, 03, 06, 09.
How much
09,
difference are there
02.
in those geoidal models?
It depends on where you are.
You can look at that as
Keep them coming.
It's always it's always occurred to me that the raw measurements you make to the ellipsoid can be used 10 years, 20 years down the road, however long down the road you want to use it. You just have to update your estimate of where your water level is at that time, whether you update your tides or your geodal model, whatever you do at that time. The archiving, I was going to ask you about the archiving. How do you archive the data? And you kind of went over that.
So flood models, tsunami models, verification, VDatum extension offshore. Somebody that I was talking to that's associated with VDatum, they were saying how the fact that VDatum kind of goes to the coast, but they don't have a good way to validate it off or doing verification offshore. So that certainly, I think, is another application there. Clearly, it still just depends on the quality of your tide model, but if you have a vessel transiting the same area all the time, maybe repeated measurements is good enough to rebuild what the tide should look like there. So this grading method is one thing I mentioned still needs improving. I actually got the least scores regression working today, but didn't have time to stuff any kind of visualization in here. So hopefully have that soon. And then the whole how to come up the uncertainty is still kind of an unaddressed topic. But so that's it. Yeah, Shock.
Looking at other users, the LiDAR community, every Chadwick 6 meeting I was in the last 5 years, the Navy is interested not using tide gauges, but predicting models in different locations over the world and the LiDAR data. Do you see a potential of using that to convert WGS data into chart data?
Yeah, I think it's all a question of the level of accuracy that people are looking for, because there are things in there like the offset to the water line of the ship that sometimes can be a really poor measurement. You might look at this and say, well, why don't we just do this with all the ships that go everywhere, and just essentially have them all record their ellipsoid height and try to figure out the water line. But I think that could get pretty tricky. I'm not saying it's impossible, but.
But if you have a depth and the auxiliary data, you're all set, and a tide model of some sort?
Yeah, I mean, depending on how many times you're transiting the area, I think, was it Jonathan who did the work with transiting?
Nathan Wardwell?
Oh yeah, it was Nathan.
Nathan, yeah.
Yep. Yeah, so I mean, it's essentially doing that. It's the same thing, really.
Sean, what did you say about the tide gauges and replacing it with a model?
The Navy in some location tries to avoid putting tide gauges in the water, just want to do a LiDAR survey, and sometimes the Army Corps of Engineers don't have tide gauges all set up. So the data is in WGS84, but not in a chart datum of some sort.
You have archive in a dotted line. Does that mean that it's not yet implemented, or what?
Yeah, we're not currently archiving ERS surfaces, to my understanding. Everything is to middle of the water.
There's been a lot of comments saying that's a really important step.
Yep.
Do you guys have in the NOAA Corps access to P codes for, I don't know what they call it nowadays, GPS surveys, base stations?
No.
No.
Thank you. I didn't think you did.
They will in the future.
I was going to
once-
say, what are the chances you'll ever get those?
Once M code is released to the
I
military.
think everybody gets.
And how accurate is that, the M code thing?
Well, M code takes
10,000+ years to decode, where the Australians have already cracked P code.
So does that mean you get survey grade accuracy without needing base positions?
Yeah, you don't need the course acquisition anymore. But the P code will only be available to commercial aircraft and maybe NOAA. It won't be available to us.
Us meaning?
Anybody other than the highest
CCOM?
priority. Well,
CCOM has access to everything.
What are
any private citizen.
Ben, you got a question?
Oh, it's so remedial. V-data, I want to know what, I missed this probably early on, the relationship between ellipsoid, V-datum, topographic heights and all that stuff. Where does that fit into that model, in those different datums? What is V-datum?
V-datum essentially is a model that goes about, I don't have any.
It's not a datum in the first place, right?
Right. V-datum basically combines the geoid, it combines models for sea surface topography and tide models so that you can convert between different datums.
Okay, so it's a conversion factor of some sort.
Conversion software
It's a
package.
toolkit. It's a toolkit.
Yeah,
it's a toolkit.
Right, it's for conversions, it's got, you know, these things that Glen mentioned built into that conversion process.
I see.
And it's going to get more important in the future because the goal is for it to absorb something called Opus, and it will be the tool to convert from any vertical datum or horizontal datum to any other one.
Because NGS is going away from supporting all their passive marks.
Yeah.
So essentially this will become.
It will become the tool.
But you
Yeah,
use it
Jim,
to-
Wednesday ill. I'm keeping
I'm keeping it. I don't trust all this stuff.
But to use V-data, you have to have a hydrodynamic model for the area. And that's, those areas that Glen showed in red were the only areas that they have.
I see.
So we don't have V-data to here, this area.
But it's scheduled.
It's scheduled coming very soon.
The issue is Alaska. I mean, that's a longer way away.
But there's a whole rest of the world too, you know. I mean,
Well, and other people are starting to develop, clones of V-datum. There's a European version, and
But it's just.
they're just a little bit different, a little bit behind us.
Yep, Tom.
You mentioned before, or Chris mentioned that tidal datums are determined by 17 or 19-year records, but they're being updated more frequently in cell places. Does that mean every year they take the last 19 years and recalculate what those datums are?
I don't know how they actually.
Yes, it does, yeah, it does. Every time they do it, they take the last 19 years.
And how
to do
frequently
it.
do they do that?
Well, they do it from time to time. As needed. It can be, it can be 10, 12 years, or it can be sooner, I think.
Yeah, Chris.
One other comment, Glenn. Something that I hear a lot is surveying on the ellipsoid.
Yep.
And as you know, and I think everybody here knows, there's not just one ellipsoid.
Right.
There are many that you could be on. And I think that terminology is a little bit dangerous because for people who don't know that, and they just say, okay, surveying on the ellipsoid, here's my transformation between the ellipsoid and mean lower low water, or whatever, and then they apply that without knowing what ellipsoid they actually started on. Obviously, they could do bad things in doing that. So, all of this I think is great, but I think in putting it out there for the general public, maybe we want to go away from this surveying on the ellipsoid, or maybe the ellipsoid asterisk, and then down below, what ellipsoid are you really talking about?
Right.
And by the way, I suspect for the work you're doing, actually I don't know this, but I suspect it's NAD 83/GRS 80.
Right. Exactly.
But GRS 80 is independent of any of the other coordinate systems we're talking about. It is the Earth ellipsoid officially adopted by the International Association of Geodesy since 1980, and there has not been an alternative since then. There are older ellipsoids that are based on older models of where the center mass of the Earth is, but the International Association of Geodesy decided in 1980 that the size of the Earth is 6378137 meters, period, and there's no ifs, ands, or but about it.
Well, back up a second. If somebody, if somebody is working in WGS 84, insert your realization epoch after that, and has elevations relative to that WGS-84 ellipsoid, and uses what Glen has just produced, which is a separation model from NAD83/GRS80 to mean lower low water, or whatever tidal datum you happen to be working with. There could be big errors associated with doing that transformation and going from a different starting ellipsoid to the tidal datum.
It all depends on how you're defining NAD83. There are many different flavors of it as well.
Yeah,
But,
correct.
but the most recent ones, the ones since they started being referred to GPS instead of transit,
Yeah.
have been tied to the International Terrestrial Reference Frame, which is the golden standard for positioning. And so it's now officially, since 1998, 2 meters offset from ITRF. WGS-84 is within 1 centimeter of ITRF. So my understanding is that GRS-80 is a size and shape of an ellipsoidal surface, the origin of which is at the center, but since NAD83 is now defined in relation to ITRF since 1998, the later flavors of NAD83 don't have a distinct ellipsoid. It's the ellipsoid that is centered at the center of mass as determined by ITRF.
I'll just say from personal experience that people, I get data from people on all different ellipsoids.
Yeah, if they're doing inappropriate transformations, but I think we're reaching some kind of consensus, at least in the last decade, that there is only one ellipsoid, and you can be offset from that, but you know what your offset is. Currently 2 meters for NAD83.
So is it ITRF 00, the standard reference frame that they're trying to reference that to?
Well, again, there are several flavors of ITRF, but those are based on different data sets, and as we progress, the transformation between, for example, ITRF 2000 and ITRF 2008 is like 1.2 millimeters.
I'm okay with that. I can live with that.
Any other questions?
Thank you.
Thank you.